We now come to the most non-intuitive part of all of 801, and arguably perhaps the most difficult part in all of physics. And that has to do with gyroscopes. And I really urge you to pay a lot of attention and not even to miss 10 seconds. Because you're going to see some mind-boggling demonstrations which are so incredibly non-intuitive that unless you have followed the steps that lead up to it, you won't have any idea what you're looking at. It will be fun, it will be cute, but it won't do anything for you. Imagine that you and I go in outer space. No gravity, we're somewhere in outer space. And we have this bicycle wheel there. And I'm going to put a torque on this bicycle wheel in this direction. So I'm going to put my right hand towards you and my left hand away from you. And I do that for a short amount of time and I let it go. It's obvious what's going to happen. This wheel is going to spin like this forever and ever and ever. I've given it a little torque. That means if there's torque, there's a change of angular momentum. The angular momentum change must be torque times delta t. And so I do this and let it go, and it will rotate about this axis forever and ever and ever. Simple, right? Okay. Now, I'm going to torque it in this direction. So in outer space, really standing still, and all I do is do this, and I let it go. Then it will rotate forever and ever and ever and ever in this direction. That's clear. Now comes the very non-intuitive part. Now I'm going to give it a spin in your direction. And now again, I'm going to torque like this. What will now happen? You will say, or you might say, I'm not accusing you for anything. You might say, well, you give the wheel a spin, so the wheel will probably continue to spin, and you do this. So maybe what you're going to see is that it will rotate like this, as it did before, and in the same time, the wheel would be spinning. But that cannot be. Because if the wheel would be spinning like this, then the angular momentum of the spinning wheel is in this direction. And if I would give it a twist, and if it would continue to spin and it would rotate like this, then this spin angular momentum would go around like this. And that cannot be because there's no torque on the system. Because once I let go, there is no longer any torque. So it is not possible for the wheel to keep rotating, and as a result of this torque that I give it, that it simply goes around. That is not possible. How is nature going to deal with that? I'll show you that on a view graph. It's very non-intuitive what will happen. And we will then also, I will also demonstrate it to you. So here is the situation precisely as I described it to you. You are, as an observer, in this direction. This is the direction of 26,100. So you are viewing the wheels like this. They're spinning towards you. That's what I will do shortly, and that's what I implied now. This is my right hand, and this is my left hand. The separation between my right and left hand is little b. So the torque that I apply is Bf. It's this arm, so to speak, times this force. And the force is perpendicular to the arm. I apply a torque for a certain amount of time, delta t. When I do that, I add angular momentum in this direction. But the wheel was spinning in this direction, you see it. And so the angular momentum of spin of the wheel is in this direction. I add angular momentum in this direction. And you see that here. So this was originally the spin angular momentum of the wheel. I torque for a time delta t, and so I add angular momentum like this. And then I stop. So I only torque for a short amount of time and I stop. That means after I have stopped, the angular momentum of the system as a whole can no longer change because there's no torque on the system. And the only way that nature now can solve that problem is to tilt this wheel in the way I've indicated here and to make it spin in this direction, and it will stand still. In other words, I hold it in my hand, the wheel. I will get it. I give it a spin. I hold it in my hand. I spin it towards you. And I'm going to put my right hand towards you and my left hand away from you. The spin angular momentum is now in this direction. So I'm going to give it a torque like so, that means up. And what will the wheel do? The wheel will do this. It's very non-intuitive. Watch it. Isn't that strange? You wouldn't expect that. I will do it again. So I'm going to torque by pushing my hand towards you. And the wheel does something completely unexpected. It simply tilts. If I torque the other way around, then the torque, of course, will make it flip like this. I'll give it a little bit more spin angular momentum. So now I move my left hand towards me and towards you, and my right hand towards me, and then I expect that the wheel will do this. And that's what it does. Extremely non-intuitive. These torques applied to a spinning wheel always do something that you don't expect. However, there is one thing that always helps me in terms of guiding me, and that is you can always predict that the spin angular momentum will always move in the direction of the torque, which is this external torque that I applied. Let's go over that again. We have here the spin angular momentum that you saw was pointing in this direction, and I applied a torque in this direction. It's a vector. And what does the spin angular momentum do? It goes in the direction of the torque. And then when I stop with my torque, then of course nothing changes anymore. And so what happens is this wheel tilts. But notice that L, the spin angular momentum, has moved from here to here. And I was torquing in this direction, so it moves towards the torque. If you have digested this, then you can test yourself now. Now we have the same wheel. I'm going to rotate it in exactly the same direction. But now I'm not going to torque like this in the z direction, or like this in the minus z direction. Now I'm going to do this, or I'm going to do this. Try now to really concentrate on what I just taught you. And try to give an answer to the following question. The wheel is rotating. I hold it in my hand, and I'm going to torque it like this, so that the torque vector is in your direction. Angular momentum was like this. Torque is like this. What will the angular momentum vector do? Move in the direction of the torque. What will the spin angular momentum vector then do? If the torque is in this direction, it will do this. It's going to move in the horizontal plane. Very non-intuitive, but that's what it will do. And I will show that to you. I'm going to spin this wheel. I'm going to spin it with a high angular momentum, high spin angular momentum. And then I'm going to sit on this stool, and I'm going to torque exactly as you see on the picture on the right. I'm going to torque like this. And as long as I torque it like this, that spin angular momentum wants to go around in the horizontal plane. And when I torque the other way around, it will go back in the horizontal plane. I'm going to torque exactly as you see on the picture there. You ready? I stop the torque, nothing happens. I torque backwards, I keep torquing. I keep torquing, I feel it in my hand, I really have to push. I keep torquing, and I stop torquing, and it stops. So the angular momentum vector is chasing, so to speak, the torque. Is that non-intuitive? Very non-intuitive? It's also dangerous sometimes. We call this motion of the stool, and in this case the motion of the spinning wheel, we call that precession. So you apply a torque to a spinning wheel, then what you obtain is a precession.